I said odd, I meant even derivative. The odd derivative is minus 1 to the k cosine of x, right? So Caleb was asking, what's the m? The m is a bound. It's assumed in the theorem. It's something that's a bound for the well, in this case, the k plus 1th derivative. Let me replace k with n for the sake of this discussion, all right? So what is a bound for the n plus 1th derivative? I mean, you guys pick any interval you like, right? Let's look at the interval. Let's say a to b, right? Just for the sake of applying this theorem. So let's let a be less than b. So you guys tell me, for x, for a less than x less than b, can you tell me what I can put here as an m? What is an upper bound for any derivative? Any derivative of sine? 1, right? So 1. So it's kind of anticlimactic, but the m for this problem would be 1. The m for an other problem, oof, that requires thinking, all right? So then what? What's that say? It says that the nth remainder centered at, you know, x naught. Let's say, we'll say it's centered at x naught. Let's let x naught equal to, for the sake of specificity here, we'll let x naught be b minus a over, good grief, a plus b over 2, right? So the midpoint. The midpoint of a and b is a plus b over 2, right? The average of two numbers, take them, add them, divide by 2, that's the middle. So the remainder term, the nth remainder term centered at x naught of x, the remainder theorem here, right, says that that is what? It is the absolute value of it is less than what? M, what is m here? 1. And then L, what's L? L here is equal to b minus a, right? It's the length of the interval. So we have b minus a to the what power? N plus 1, and then we divide by n plus 1 factorial, right? So the remainder centered at x naught of x for the sine series is bounded above by b minus a to the n plus 1, divided by n plus 1 factorial. What happens to that as n goes to infinity? Notice here, yeah? It goes to 0. Now, why do you say that?
Because factorial matches exponential.
Yeah, the factorial beats exponential, right? So, yeah. So this goes to 0. Now, to prove that, of course, would be more involved, but we have done these kinds of limits before, right? We've studied things like 5 to the n over n factorial, and we've seen that you can make an argument that shows that that goes to 0 by the squeeze theorem for n sufficiently large. So the same is true for b minus a. It's just a number. Whatever number it is, eventually n factorial wins. Therefore, the remainder term for sine goes to 0 if we look at the Taylor series for sine centered at x naught. But this a and b were arbitrary, and as was the midpoint x naught, right? So this proves that the Taylor series for sine converges to sine at an arbitrary center point, essentially. I mean, if you look at it, a and b are arbitrary. You can prove that sine you pick any midpoint you like. I can make it any point you like on the real line, I can make it the midpoint of an arbitrarily large interval, right? If you think about it, it's not hard to see. Therefore, sine is equal to its Maclaurin series. So sine is an analytic function. If you understand this, it's pretty easy to see the same is true for cosine, right? How would the proof of this look like for the exponential? It's a little bit different, right? But I promised I wasn't going to get into this too much in this course, so I'm going to stop there, all right? But if you're a math major, it would be a smart thing to try to figure out how this goes for the exponential. It's a little bit different. It's not so nice for the exponential because you can't just say the derivative of the exponential is bounded by 1, right? I'll tell you this much. If we were looking at the exponential, right, and it was on a less than x less than b, then you could say this, that e to the a is less than the nth derivative of x is less than or equal to the e to the b, because the nth derivative of the exponential is the exponential. So you'd have e to the a and e to the b as bounds for the exponential's nth derivative, and so you could use like the maximum of, well, probably e to the b. You could use e to the b as your m. And then when you look at the formula for Taylor's remainder, you'd have like e to the b times b minus a over n plus 1 factorial. But what's the story? What's the fate? If you have e to the b times b minus a to the n plus 1 over n factorial, guess who wins? N plus 1 factorial. Notice that the b, e to the b is not a dependent on n. It's just e to the b. It depends on b. It doesn't depend on n. So it's, again, just a number times b minus a to the n plus 1 over n plus 1 factorial. Therefore, the exponential is analytic everywhere as well. Forgive me for not writing it down, but I don't expect you to replicate it on a test or something. Logically, it's something we should talk about, but it's, like I said, I think it's a little bit beyond this course, that part of this. So we just have been assuming this, that our function has power series representation. Now, look here, I have pictures, guys, in the notes. So you might wonder, what does this matter? Well, this matters, like here, for example, let's just talk about a couple examples. Here I have a 5th order polynomial, 6x to the 5th plus stuff, right? And I calculate the derivative, and I figure out that 0, 2 is a critical point. I calculate second derivative, and let's see here. I said I'm going to show that the quadratic Taylor polynomial T2 of x is this. It gives a good approximation for f of x in the sense that the maximum error is essentially bounded by the size of Lagrange's term. So if I'm looking for using the quadratic Taylor approximation to talk about the function, the error in that is bounded by the third derivative, by Lagrange's theorem, Taylor's theorem with Lagrange's form of the remainder. So I calculate the third derivative to be this, and the fourth derivative is that. Now, I calculated the fourth derivative in order to see that the third derivative is increasing. See, if the fourth derivative is positive, that means the third derivative is increasing. If the third derivative is increasing, then that means that the value of the third derivative at the left endpoint is less than the third derivative is less than the value of the third derivative at the right endpoint of the interval of consideration. So calculating the fourth derivative is helpful in that regard. Because if I'm going from minus 0.1 to 0.1, and I have that the fourth derivative is positive, that gives me that the third derivative at the endpoint is less than the third derivative in the middle, is less than the third derivative at the other endpoint. So that bounds the third derivative to be negative. What does that mean? Well, if the third derivative is negative, I have then that, well, excuse me, third derivative is like this, so I get minus 92 and minus 20 before and after, which means that my m for the third derivative is 92.4. So finding a bound for the mth derivative is generally, it requires analysis, all right? In this case, I figured out 92.4 works, provided I'm looking at, plus or minus 0.1 from my center, which is 0. So that told me that I should expect an error bound of 4 m delta cubed. Delta is my delta here is, let's see here, 2 delta is L. That's where this 4 is coming from, right? L is equal to 2 delta in this example. And so I work that out, I get 0.123. So supposedly, the error in the quadratic Taylor polynomial is at most 0.123 if I'm within plus or minus 0.1 of the center point. And here's a picture of how it went. So what you're looking at is a zoom in. I zoomed in here, and I actually graphed plus or minus 0.123 from the function, and I've graphed both the function, which is in red, and the Taylor approximation, quadratic approximation to it in green. And as you can see, my upper bound on the error is not at all tight, right? Like I'm not even, it's very generous. If I say, you're within 0.123, all my customers should be very happy because in fact, it's about 10 times better than that, right? So kind of like Amazon, you're going to get your package in 3 weeks. You get it in a week, you're like, yeah. So anyway, but as you can see, if you get past its realm of applicability, then the second quadratic approximation to the function is no longer reasonable, right? So it's tight with the function if you're close. If you wanted to track this polynomial further out, you'd have to take more terms. Now, in this case, it would exactly match it if you look at Taylor's polynomial, say of order 5. Like that is a 5th order polynomial we're modeling. So if I took Taylor's polynomial for order 5, it would be exactly the same. It's very silly. This is often a test question. Find the Taylor expansion for f of x equals x cubed centered about 2. You can do that. It will be a 3rd order polynomial. So anyway, so here's sine of x. And so I figure out that the error in the kth Taylor polynomial for sine is bounded by 2 to the k plus 1 over k plus 1 factorial when I run through it. Here m is equal to 1, right? And so in this case, I started looking at the errors for different orders. So I got like error was 2, error was 4/3, 2/3, 0.25. By the time I get to the 5th one, 0.1. So if I use the 4th Taylor polynomial, I'll get within 0.1 of the truth. And so here's a graph of that. You're looking at sine is the red curve, right? And the 3rd Taylor polynomial is the green curve. And as you can see, we're within 0.1 if we go from plus minus. I'm just looking at minus 1 to 1 for the sake of graphing. All right? What if you want to do better? Let's see here. Now, this one, I'm going all the way to plus or minus 2. And I've used the 9th Taylor polynomial. The 9th Taylor polynomial works longer. It tracks sine even further, right? And if you keep going higher, you'll get further and further. Let's see here. Oh man, well, maybe that was it for my pictures. Here's another one. I may have just skipped past it, my bad, but let's go on. This one here, suppose you're faced with the task of calculating the square root of 4.03. You're in the robot holocaust, right? The calculators are evil and such, so you gotta do it yourself, right? So imagine we're at the moment we still have these calculators. These are safe, right? They're not part of the net. They can't be accessed by the central intelligence, right? Although of course we all have cell phones, so the NSA is listening to us, right? But yeah. Actually, who cares about the NSA? I'm kind of more worried about Amazon. But honestly, yeah. So, I mean, seriously, if they decide to ruin your life, what power do you have over them? Almost none, really. I mean, they've destroyed whole corporations in the last decade. It's disgusting. Okay, I digress. But Amazon's wonderful. Amazon's great. Love Amazon. And Google. Google's great too, while they're listening. So here I calculate the 2nd order quadratic approximation to the square root. And I get this. And I bound the error looking at the 3rd derivative. And this shows that it works. All right. So anyway, what I'm trying to tell you here Oh, and then here's that. Oh man, I had a picture in here somewhere. Must have skipped past it. Well, anyway, we're done for today. So, should we have a quiz?